In this clip, we're going to look at orthogonal decomposition. So in particular, if I've got some vector u and some vector v, then what I want to do is I want to find out the components of u sort of with respect to sort of the coordinate system given by v. So I want to think about there being a coordinate system where v is spanning one of the branches and the other branch is orthogonal to it. So this is what I mean by the orthogonal decomposition. So moving over, I'm going to look at projecting u onto v to find some scalar multiple of v here. So this is some some vector parallel to v, and then also there's going to be some parallel some vector that is orthogonal to v. And so then I can see u in terms of the v component along here, and then also in terms of the orthogonal component along here. And so the sum of these two green vectors will give me u. That's the thing that we're looking for. So to write this down, let's see. So we're going to have w orthogonal to v, and then we're going to have u equal to some scalar multiple of v plus w. Okay, so from that we can see that w is going to look like u plus cv for some scalar c. And now I just need to find the right one. So how do we choose c so that u minus cv is orthogonal to v? So the picture that we should have here, let's draw the picture of what's going on. So it's something like this, and so we've got this guy. Let's see, so I'm going to put this over here, and I'm going to make it dotted, and we don't know where this guy is. So these are possibilities here. So we've still got our u over here, and then here's our v, and then the points on this line right here are u minus cv, as c varies from something small out to over, maybe I'll just grab this guy and make him long, over here where c is big. Okay, and so these are all the different points in between. And we're looking for that magic value of c that finds us the green line that's orthogonal to the blue line. All right, so let's see. So this means we need to have u minus cv orthogonal to v. And so what can we do with this equation? Well, we can use linearity in the first slot. So this becomes uv minus cvv. And then I just need to solve that for c, and I get uv over vv. All right, and so this is the same thing as inner product uv over norm squared v. And so this is the length of the orthogonal projection of u on v. All right, now we're getting somewhere. So that's going to be the magic value that tells us where we can find this guy here. So the length of this one is that guy. All right, so we have just actually proved a theorem. So for U, V in an inner product space capital V, where V is a non-zero vector, we have the projection of U onto V is going to be UV over VV times V, and the length of this guy, this is maybe redundant at this point because you could just find it by taking the magnitude of the thing in the previous step, is going to be magnitude UV over norm V squared. So, and also, if we define W to be equal to U minus its projection onto V, then W is going to be perpendicular to V, and the projection plus W is the orthogonal decomposition. Orthogonal. Whoops, and I just ran out of space there. Orthogonal decomposition of U with respect to V. And things get much nicer if you were dealing with unit vectors. And so in the sections to come, a lot of times if we're projecting onto something, we'll make sure that something is a unit vector. So just by way of comparison, if we look at UV, the inner product, over norm V squared times V, then this is the same thing. So I can divide up, basically I've got two factors of 1 over magnitude V to deal with. And I can match one of them with V, and I can match the other one with the V inside by using linearity in the second slot. Well, conjugate linearity, but in this case it's a real number, so it doesn't matter. So in that case, it looks like this. So this is the same thing, right? So this, if V is a unit vector, and now I've already used U and V, and W is used for something else. So let me call my unit vector Q for lack of anything better. It takes this very simple form. So this is when Q is a unit vector. Maybe I'll make that a note. There we go.